Welcome to the ideal gas law lesson. So ideal gas law assumes that gases are performing ideally at low pressure and at high temperatures. Since usually a low pressure means it's a big area, and so as we've seen, when you decrease the amount of area or volume, there's going to be more pressure, and pressure was notated as the amount of collisions. And so when you have these collisions, okay, you have high temperature, kind of balances out the low pressure. And for gases is where intermolecular forces are basically non-existent, and these have negligible volume compared to the container. And so the ideal gas law equation is going to be pressure volume equals nRT. So the P is pressure, the V is volume, N is the number of moles, this is the R constant, this is temperature. So the conversions, plus 273 Kelvin, if not already in Kelvin. And for volume, convert to liters. So that's common ground. So let's just kind of draw this out. So these collisions would sort of happen more quickly since the temperature is greater, although there isn't as much since it's ideal, right? So just to give an idea. Now let's start by solving this first example. A 5-liter container holds 0.25 moles of helium gas at a temperature of 300 Kelvin. Calculate the pressure inside the container. Okay, so let me just write out. So since this is ideal, I would always try to go for PV equals nRT. So we kind of see what we're given. We're trying to find the pressure. We're given the volume. So 5.0 equals number of moles, the R value, and we also have the amounts of temperature, which is 300 Kelvin. So to solve for that, just plug it into the calculator, dividing that value by 5.0 to get roughly 1.23 ATM. So that's the first question. So these questions aren't really that difficult. It's really just about the process. A sample of oxygen gas at a pressure of 2.5 ATM and a temperature of 350 Kelvin contains 1.2 moles of gas. What is the volume of the gas? So let's use our equation, PV equals nRT. we were trying to find the volume. So in this case, when we were trying to find the volume, let's plug in these values. So 2.5 ATM is equal to, the number of moles is 1.2. The R value is still going to be 0.02821. And we also have 350 Kelvin. So now it's really just about the plugging and chugging. So 1.2 times 0.0821 times 350, divide that by 2.5, you get roughly 13.8 liters. So let's try this second to last example. A gas is held in a 10-liter container at a pressure of 3 atm and a temperature of 400 Kelvin. How many moles of gas are present? So for this one, we will do it write out the equation just to make things easy. And we realize we need to solve for the number of moles. So plug in these values, 3.0 times the volume, which is going to be 10 liters, equals number of moles, the R value is 0.0821 times the temperature, which is going to be 400. So be careful, the R value can change. It's not always going to be 0.0821. It's only specific for ATM is when that's the case, so it can change. So to calculate this, we would have 30 equals, and we just have to multiply these values out. And so you get roughly 0.91 moles. So let's try this last example. A sample of nitrogen gas is at a pressure of 2.5 atm and a temperature of 300 Kelvin. Calculate the density in grams per liter. The molar mass of nitrogen is 28.02. So in the past few problems in this video, we've been using PV equals nRT. But notice how there's no density and there's no molar mass in this example. So we have to switch gears and we have to use this different formula, which is going to be right around the same. So it's actually going to be the molar mass is equal to dirt over P. That's how I remember it. So pressure is on the bottom. So the density, the R value, and the temperature. And so since we are trying to find the density, we have to isolate these values. So let's just isolate density just to make things easier. So density, so the molar mass multiplied by the pressure is equal to the density times the R value times temperature. And then divide those values. So density would be equal to molar mass, pressure, over the R value times the temperature. So now our lives are so much easier. All we have to do now is plug it in. and plug it into the calculator. So the molar mass is going to be, as stated already, 28.02 times the pressure, which is 2.5, dividing that by the R value, which is 0.0821 because it's ATM, and the temperature was already in Kelvin, which is 300. So now you just have to divide those. So density is going to be roughly 2.84 grams per liter. So thank you for watching this video, and I'll see you in the next one.